Right now, somewhere between a river and a mountain, a machine is spinning and sending electricity toward your home. In the next hour, you will use some of it, maybe to boil a kettle or charge a phone. And here's the strange part. The power station that spun that machine did not send you a single electron, not one. The electrons in your wall socket were already inside your walls before that power station was even built. They have been sitting in that copper for years, and they are not going anywhere. So how does the energy actually reach you? If you asked someone to explain electricity, they would probably describe something like water in a pipe. A pump pushes water along, the water carries energy, and it comes out of your tap. Press the same person on the electrons in a power line, and they would tell you the power station shoves those electrons down the wire the way a pump pushes water through a hose. That picture feels right, and for a long time even trained engineers built the grid around it. It is also wrong, and in a way that once doomed the most ambitious cable ever laid across the Atlantic. Let us start with what is actually inside those overhead lines. The power that reaches your home is alternating current. The electrons in a high voltage wire do not march from the power station to your house. They vibrate. In North America, they are pushed one way and then pulled back the other way, 60 times every second. In Europe and much of the world, the rhythm is 50 times a second. Each electron wiggles a tiny distance and then snaps back, so that after one full cycle it is exactly where it began. Measured across a whole second, it has gone nowhere. That is the first crack in the pipe story. It gets stranger when you look at how slowly electrons move, even when they are going somewhere. In a direct current circuit carrying a series current, the electrons creep along at about 1/3 of a millimeter per second. A garden snail covers more ground than that. If you stood beside a wire and tried to raise its electrons, you would win by a landslide. And yet flip a switch and the lamp comes on instantly. Something is clearly moving far faster than the electrons are, and whatever it is not inside the metal. There is a second crack in the pipe story, and it is hiding inside a metal box on almost every street corner. Transformers. The grid does not run a single continuous wire from the generator to your home. Along the way, the electricity steps through transformers, and inside a transformer the wire literally stops. One coil of wire ends on one side, a separate coil begins on the other, and no metal connects them. The two coils only influence each other through a magnetic field. If the electrons were what carried the energy, the whole journey would stop dead at that first transformer. So something else must be leaping across the gap, and the grid steps the voltage up and down through these gaps on purpose, because pushing power over long distances works far better at a very high voltage and very low current. That something was worked out in 1884 by an English physicist named John Henry Poynting, and his answer is so counterintuitive that it took the world decades to accept it. The energy in an electrical system is not carried by the electrons inside the wire. It is carried by the invisible electric and magnetic fields in the space around the wire. Poynting showed that whenever an electric field and a magnetic field overlap, energy flows through the space where they overlap, in a direction at right angles to both of them. Around a power line, the electric field points outward from the wire, and the magnetic field circles the wire like a ring. Combine those two fields, and the resulting flow of energy runs straight along the path of the wire, but out in the air and the insulation around it, not inside the copper itself. That changes how you should picture your toaster. When you switch it on, the energy does not pour in through the cable like water through a hose. It closes in on the heating element from every direction, arriving through the space that surrounds the wires, and lands on the element where it becomes heat. The copper is not a pipe, it is a guide rail. It shapes and steers the field the way a riverbank steers the water flowing beside it. Now pay attention to the direction here, because it explains the next mystery. Alternating current reverses 50 or 60 times every second. If the current keeps flipping, why does the energy still flow from the power plant to your house and never back again? Because the electric field and the magnetic field flip together. Reverse both at once and the direction of the energy flow stays exactly the same. It is like multiplying -1 by -1. The electrons keep shivering in place, and the energy keeps moving one way regardless. If you have been enjoying this look at how the power grid actually works, please subscribe. We dig into the hidden engineering behind everyday life every single week. While the mathematicians were settling all of this in the 1880s, something far more concrete was proving it at the bottom of the Atlantic. In the 1850s, engineers set out to lay the first telegraph cable across the ocean. To protect the thin copper core, they wrapped it in insulation and then armored it in a jacket of iron. The iron was meant only to strengthen the cable, but that same iron jacket interfered with the electromagnetic field around the conductor. The cable began to behave like an enormous capacitor, storing charge instead of passing a clean signal. Dots and dashes that left one shore sharp came out the other end smeared and stretched. On the 16th of August, 1858, the first official message crossed the Atlantic. It was 98 words long, and it took 16 hours to transmit. That works out to about 2 words every 20 minutes. Within 3 weeks, the cable had failed completely, burned out by the very voltages meant to drive it faster. The failure triggered a long argument about what actually carries a signal down a wire, and the winning answer came from a largely self-taught engineer named Oliver Heaviside. The energy and the information travel in the field around the conductor, not in the metal itself. The first Atlantic cable died, at least in part, because it had been built around the wrong mental model. That lesson reshaped the entire grid, and you can see it every time you drive past a row of transmission towers. Those power lines are not strung high in the air by accident. They are kept far above the ground because even slightly damp earth conducts electricity. If the wires sat on the soil, the field around them would leak into the ground and bleed away. By hoisting the conductors high into the air and holding them away from the steel tower on long strings of glass and porcelain insulators, engineers give the field a clean gap to travel through. Air is the insulation. The empty space around a power line is not wasted. It is the part doing the actual work of carrying your electricity. So the next time you flick a light switch, remember what is really happening. The switch closes, the electric field rearranges itself down the line at almost the speed of light, and power arrives at the bulb from the space around the wire rather than through the copper. The electrons were there all along, shivering in place and doing almost none of the work. The wire is a guide. The energy rides the field beside it. That power station never sent you a single electron, and it never needed to.